please let us know. I wonder if I'm not hearing I'm not hearing any sound at all. I'm wondering if I'm not.
Watson, I can volunteer to take notes.
Perfect. I hear you. Thank you for that. Thank you very much indeed. Okie doke. Welcome everybody to IETF 111 and welcome to the Pearg meeting. We have a note well for everybody, the regular note well. Of course, the session is being recorded as well, as per usual for IETF. So please note that. This is our agenda for today. Blue sheet's automatic now. The other chairs will actually be watching the chat, so I don't believe we need a JavaScribe, and we already have a minute. Thank you very much indeed. So before we get started, requests regarding the agenda today. No, if everybody is happy with that agenda, we will move forward. So the agenda today is a couple of updates on drafts. We've got a very brief mention of the IP address privacy draft, and then Mallory will present on safe measurement, the update that she's done recently. We've then got 4 presentations today, one on website fingerprinting in the age of quick, one on improving Tor latency, one on private relay, and then our final presentation is on Flock today. So I will start by just giving a very brief update on where we are with the IP address privacy draft. So this is a draft that came out of the 2 recent interims that we held on various aspects of IP address privacy. We did not get it published before the cutoff, and in fact it did appear a couple of hours ago. Hopefully you've seen there was an email to the list with the first version of it, and there's also a GitHub repo if you're interested. Matthew and Luigi have provided PRs so far. At the moment it's a fairly skeleton structure with headings and placeholders. Matthew and Luigi are going to add more content over the coming weeks, but we are still looking for other contributors on this, particularly on the use case sections on which there were a lot of presentations during the interim. So if you're interested in working on that, please read the document and please let the chairs or the other authors know. Okay, so that's just a brief overview on that. So I will now pass over to Mallory to do a presentation on the safe measurements draft. So let me stop. Hey Mallory.
Hey everybody. Thanks, Sarah.
Okay. So do you want to share your own screen? Yeah.
That's all right. Okay, I clicked all the buttons.
Yep, we see you. Go ahead.
Great. Hey, everybody. So I've recently agreed to take on some of the work for this draft, which is a working group draft, or a research group draft, rather, on guidelines for performing safe measurement on the internet. Ian Lermouth and Grover from CIS India. They've worked on this already. I just very few changes in the latest version that went up right before the doc freeze. So I want to just go over those and give you all an overview of where this document's at in case you'd like to help, because I think it's an important document, and I think, yeah, the research group should continue to work on it. It fills a major need. So yeah, I've already mentioned the authors. The goal of the draft, overarching goal, we can discuss whether or not it's reaching that goal. So for industry and academia, presumably others, anyone doing measurements as part of their research on the internet and its use, we're trying to describe some guidelines to ensure that those measurements can be carried out without violating user privacy. That's why this is in this research group. So there's some interesting stuff around scope that's at the beginning of the draft. Is actually really important. I think that it's there, and it's one of the things that I strengthened in the last version with some of these. So yeah, it's not meant to be a substitution for ethics review. In fact, I think it's important to actually just complement ethics and state that rather than try to sound like it's an ethics consideration. I think it's not. It's also not legal advice, of course. And then it tries to also, I think, define better what internet measurement scope means. So the network, its hosts and links, or its traffic. I'd be interested in people in their assessment of that scope definition. And then the last thing is it needs to identify the user and who it's being safe for. So that would be an individual or organization whose data is used in communications over the internet, and that might be swept up in measurements of the internet. So in 3 parts is the main structure of this document. It talks about consent as a concept. We could discuss whether or not meaningful consent can be gotten, and if that is enough to really, if it actually creates safety and privacy preserving. Then the second piece is around safety considerations. So this goes into depth in a few different subtopics. So isolating risk with test beds. There's a part about being mindful that you're maybe encroaching on others' infrastructure. An important piece on data minimization, which I don't think we talked enough about these days. Not creating it. If you've got it, get rid of it eventually, that sort of thing. And then masking data, which could be all kinds of different techniques within that subsection. And then lastly, there's a section on risk analysis. That's the main, those are the broad strokes. Oh dear, that looks terrible. This is the table of contents. Yeah, you can see then those 3 main parts are there, and then the subtopics, and then the subtopics there. So just, you know, if you wanted to have an overview. Unfortunately, the draft at the moment isn't produced, like the XML is not producing properly a table of contents in the draft. So this I made by hand and then displayed poorly in the slide, sorry. So yeah, the last time it was presented, which if I'm not wrong was maybe 108 or 109, Ian had been working on adding a, or in Gershabot as well, adding a section on responsible disclosure. So there's some important then stuff that followed on from that open issue that turned into talking about accountability and transparency of any measurement research project. Then there was also some need to cite some research that aligned very closely with the goals of this discussion of IP address, and then also like this thing that I mentioned in the beginning, like, you know, safety is not equal to ethics. Can we find a way to align with ethics efforts and be complementary to them, but not actually pass this draft off as ethics and measurements? So yeah, that's essentially what's been done since the last version as well, since 04 over 05. And that's really it. So the things that are still open in GitHub, which you can check out, needing to do a better job of the responsible disclosure piece. Then all available disclosure
I think your audio dropped for a couple of people just on the very last slide. That's okay. So if you could just sort of repeat.
I'd be happy to go back. Is it this one then? I think maybe the last thing I was saying was just that, we want to make sure that we're citing and lifting up other efforts that are similar to this, or bring in learnings, especially as they fit into the table of contents. So if you know of resources, especially the section potentially that we should be quoting from or referencing, please open an issue with that information. But even better than that, right, would be a pull request.
So the chairs also want to thank Mallory for picking up this draft, because it had originated a while back, and unfortunately the authors weren't able to work on it at that time, and Mallory's now picked it up. So we're hoping that with the latest update she's done, we can get some more reviews and we can get input and actually get this draft moving forward. So I think, Mallory, would you be interested if there are other people who want to contribute and help you pick the document up right now? Is that something else to appeal to the research group for?
Yeah, indeed. If you want to do pull requests, that's also, if you want to do substantial edits or just get on a call with me, or we can talk through changes you want to make, we can make you can do it directly to the repository as well. Just let me know. I should probably drop my email if you don't have it. Also, it should be on the draft itself. But yeah, I'd love some help. I am going to finish this one way or another, but for people who are particularly interested in this, especially some of the more interesting topics, I think we'll be able to get into discussion and debate in the future once there's like what I would consider to be a complete and full draft, because there's a bunch of sections that are just kind of placeholders. But yeah, I love debating the idea of consent and meaningful consent in these contexts, because it's really hard to get anyway, and we're in some lower layers. So let's talk through some of those things.
Yeah. I see Stephen in the queue.
Great.
Do you want to go ahead and ask your question? I think, Stephen, we're not getting your audio. I think you should have it.
Okay, video. So I presume audio is working too. I think that topic of consent.
Some freeze frame video.
Two thoughts on that. One is
snippets of Stephen.
stopping video will help audio. Does that work better?
Yeah, just speak again. It was flaky. I think everybody's having problems with audio, which is a shame. Okay, do you want to give that another whirl, Stephen?
Okay, let me try change.
Yes, indeed. Welcome to IETF, the first session. Okay. So Stephen's going to type a quick question. If there's anyone else who wants to step up to the mic while he's doing that.
I haven't missed anything yet.
But I I agree around the question of consent, because I think often in IETF documents, particularly around protocols, it isn't the right place for IETF or IRTF to discuss consent, and having somewhere we could actually work through some of those ideas would be very helpful. So, yeah, I'm going to drop my video because you don't need to see me. So we're waiting with bated breath for Stephen's questions. Here we go.
Brad, did you have a question?
Yeah, so I can actually voice Stephen. What he says is it would be good to include examples of when that was handled well and when badly. And I like already the model of case studies, although I would probably rename them as examples instead of case studies. They're not complete enough, I think, to be considered a case study, and to also not stack them in the hierarchy the way they are. But anyway, I like that idea, Stephen. And then he goes on to say, I think this document might end up being a model for other IETF documents that mention consent, so it should be done carefully. I think it should. I think what you mean by carefully or safely is that it should be done very conservatively and not giving the idea of user consent free reign to do a lot, because I don't think there's a great deal of possibility for meaningful consent. But we can, yeah, we'll dive into that, and we can do that by looking at examples. So yeah, if you want to try audio, I'd be happy. Go ahead, I guess.
Okay, we're still not getting you, Stephen. No, I think we're not. We are not getting you. Oh, hold on. Speak up again.
Okay.
Okay, you're
Yeah,
there,
so
but
I
very
was trying
quiet.
to say that oh, for God's sake. I can still type, or I can yell first.
Just shout.
What I mean is carefully is that other people will use text here as a model. So be aware that we don't want people doing carelessly copying this.
It's a really good point. Just to answer in the chat, I think, yes, examples will work well. I think we have plenty of very good internet researchers that participate, internet measurement researchers that participate in the IRTF in particular and the IETF more broadly, that we can look and read their methodology and ask them if we have questions. If it's not in their literature, we can use those examples. I'm not sure that using consent approach outside of this context will be helpful. I think in general, right, like there's an ethics consideration around how you get consent from people participating in your studies. But I think what we're trying to articulate here is that it's difficult when, you know, folks' internet traffic is not, it's not the same as, you know, being in a qualitative study or things like that. So I think we have to, yeah, we'll look for examples. We want it to be as I think applicable to this particular field as possible. But anyway, thanks so much, everybody. Yeah.
Brad, I think you have a question. You've been very patient. Please go ahead.
If I'm not sure why you think I do, is it because I'm showing a video?
You're showing video, sending audio.
Okay. Well, that was, sorry, I'm just catching up with the protocol.
Okay.
Neat. I think that's it.
Yep, I think we're done.
Yeah.
Thank you
Yep.
for all the comments
Okay.
on that, and follow up on the list if you're interested in contributing.
Yes,
Okay.
please.
Thanks, Mallory.
Thanks. Yep. Bye.
Thank you. Okay, next up we have Jean-Pierre Smith, presentation on website fingerprinting in the age of quick. Is Jean-Pierre. So let's, okay, you should be getting your preloaded slides, hopefully. Are they appearing? There we go. Okay.
Oh, is that blurry for just me or for everyone?
It's a little bit. Do you want to just try the next slide? And
See, yeah, everything is actually pretty blurry. That's strange and wrong. I will try.
Do you want to try and show your screen?
I'll try that, yeah.
Yeah. Okay. I think
Okay.
I need,
Is it now sharing? I can no longer see.
Trying to grant it's telling me the slots are taken. So don't know if we need
Perhaps one
to
second.
revoke.
Stops. Okay.
Yeah.
There we
so
go.
we need to do that. No. Okay. Here we go again.
Okay. Great.
That's much clearer. Thank you.
Yeah, great. So, hello everyone. My name is Jean-Pierre Smith. I'm a PhD student at ETH Zurich, and I'm pleased to have been invited to share with you today our work on website fingerprinting in the age of Quick, which was presented, I believe, 2 weeks ago at the Privacy Enhancing Technology Symposium. And this is joint work between, among myself, Professor Pratik Mittal of Princeton University and Professor Adrian Pearg at ETH Zurich. And so, as I'm sure many of you can remember, in the early days of the internet, if an adversary was interested in identifying what content a user was browsing or viewing on the internet, he could do so by simply observing the URLs, the GET requested data, etc., in the packets as well as the destination IP address. To counteract this, of course, SSL TLS was added to the network, and now the content was no longer encrypted. However, there are still the certificates which are exchanged between the user and the web server, and tags such as a server name indicator, which still reveal to the adversary what a user is browsing or what a user is viewing when he's browsing the internet. Because of this, privacy-conscious users move towards using privacy-enhancing technologies like VPNs and anonymity networks. And now most of the information which was available to adversaries is no longer there. And in an ideal world, or in a perfect world, this would be the end of the story. Unfortunately, this communication still leaks metadata, so packet sizes, timings, and the directions of the packets. And this metadata forms the basis of a slew of attacks called website fingerprinting attacks, which are what this work is based on. And so essentially, in a network-based website fingerprinting attack, an adversary who is interested in identifying what a user is viewing, what web page a user is viewing over some encrypted channel like the Tor anonymity network or the VPN, etc. He sits in the network on this encrypted channel, and he observes a sequence of packet sizes, timestamps, and directions. From this metadata, he extracts a set of features. This can be things like the total transmission time. It can be the total size of the transmission, or the histogram of the packet inter-arrival times, etc. And he extracts these features and he passes it to some classifier, an algorithm that will attempt to identify for this given set of features, or for this metadata, which web page is being leaked. And here, usually the adversary is interested in a set of web pages. So he's interested if the user visiting wikileaks.org, YouTube, or Facebook, etc. Or he would like to know if, well, this traffic trace is not anything I'm interested in, so we can discard it. It's other, I'm not interested in this particular visit. Now, there has actually been quite a number of work in the website fingerprinting, in the website fingerprinting literature, showing that website fingerprinting is possible on anonymous networks like Tor. It's certainly possible on regular browsing traffic. But most of this work has focused on the TCP or Tor over TCP TLS setting. At the same time, however, the web is undergoing the transition, and as most of you know, and that transition is towards Quick for delivering web content. Now, most of you are, I imagine, already familiar with Quick, but Quick there are a number of differences between Quick and TCP, which will likely impact the website fingerprinting topic. For example, Whereas with a TCP connection, there is a single byte stream between the client and the server. This is now multiple individually flow controlled byte streams, which affects this affects the resulting image of the traffic on the network, moving from this one flow per connection to multiple flows inside a single connection, which are all sharing this one flow level, this one congestion control, as well as this connection-based flow control. Furthermore, one of the steps that an adversary would take when he collects the data from the network is to clean it up. So he would remove things like TCP acknowledgements and other control messages, and this would aid him in performing that fingerprinting. This is not as trivial as it is in TCP and TLS, since QUIC's packets are more of QUIC's packets are encrypted. Additionally, due to QUIC's faster connection establishment, features in a connection, such as, you can imagine the connection, an adversary looking at the connection will see bursts of packets going in, going out. These are shifted in time when going from one protocol to the other. And finally, before in this TCP-only internet, we had the situation where when an adversary observed traffic on the network, which he believed was which he knew or had belief that it was browsing traffic, web browsing traffic, then he could be quite certain that it was mostly TCP traffic. And this is no longer the case with QUIC, because now even though the web page or the main web page or the main HTML page may support QUIC, dependent resources to load that HTML page may not support QUIC and may need to be loaded over TCP. And so what the adversary is now seeing on the network is actually a mixture, even for a single web page load, a mixture of QUIC and TCP connections. And so given these such differences between TCP and QUIC, the question we sought to answer in this paper is how might website fingerprinting change given this transition in the web from TCP to QUIC? So to do that, we essentially, coming from the previous presentation, we collected a quite large data set by scanning and downloading web pages from a large number of web servers. So we emulated what the adversary would be doing to set up his website fingerprinting attack. And in our setting, the adversary was located on a WireGuard VPN with connections to New York, Frankfurt, and Bengaluru, India. And we emulated the user by using a browser. We didn't use live user traffic for this because we need the ground truth as to which web page the user is actually visiting. And here we allowed the user to visit the web page using only TCP or using these web page requested with QUIC, whereas there could also be TCP connections within that overall flow of communication between the user and the web server. We then created a data set from this, and so in total we had some 117,000 samples. So we downloaded 117,000 samples of web pages, of which 100 web pages were what we call the monitored web pages. So these are the web pages which the adversary are interested in identifying. And for these we collected 20,000 samples. So this was about 200 times we loaded each web page using the browser. We then, additionally, we also collected some 16,000 unmonitored web pages, and this allows the adversary to train his classifier to get a feel for what is not one of the monitored web pages, so what everything else in the internet looks like. And here we collected 6 samples per, yeah, is that right? No, that's not right. 1 sample per protocol per gateway. There are 2 protocols, 3 gateways. So yeah, 6 samples per unmonitored web page. And that formed the bulk of our data set across these 2 protocols. We then train a number of classifiers, many of them deep learning classifiers, and their task is, given these features that we've downloaded, to identify the web page. And so the first question that we measured recall and precision. So for those of you unfamiliar with this topic, so essentially what we measured is of the fraction. So there we have the data set, and some of the samples are the ones that the adversary is interested in. These are the monitored samples. And when we pass this to the classifier, what fraction of those monitored samples does the classifier actually detect? That's the recall. So of 100 monitored samples, does the adversary detect 80 of them, which is 80% recall, or does he detect only 15 of them, 15% recall? I know we use precision. I won't get into the detail of this variant of precision which we used. However, so what precision essentially answers is if the classifier says that these 1,000 samples are all monitored web pages and should be blocked or should be logged, and or should be logged, what fraction of those 1,000 claims were actually correct? So the first question we sought to answer was, if an adversary is in the setting where the web page where Quick has been deployed, the web pages that he's interested in tracking or identifying may be downloaded with Quick. However, he has not adapted to this setting because, well, it's the same web page being downloaded. The protocols are similar congestion control algorithms, similar loss detection and recovery, etc. So why should the adversary in this case update his classification setup? And here we ask, is he actually able to still detect these visits that occur using the Quick protocol? And what we found here actually is that the underlying transport protocols matters, and it matters greatly. So these are precision recall curves, and for those of you, again, who are unfamiliar, the goal of the adversary is to have his classifier be somewhere up here, because in the top right corner of the plot, he's achieving both 100% recall. He's identifying every single monitored web page which comes through the monitor, and he's doing it without making any mistakes. He has 100% precision. And what we found is that when the adversary does not account for the fact that a web page may be downloaded with the Quick protocol, a web page that he's interested in may be downloaded with the Quick protocol, he can suffer greatly in terms of recall. If you consider, for example, the VAR CNN classifier, which is one of these deep learning classifiers, when it was achieving near 100% precision and recall on TCP samples, it was achieving less than 4% recall on the Quick samples. That means over 96% of the Quick samples were actually evading the adversary in this setting. So the adversary, given that the web is transitioning to Quick, the adversary must now account for that in his procedure, in his machine learning classification, in his attack. Otherwise, he will miss visits to the web pages. Okay, so the next question we sought to ask is, perhaps this is because Quick is somehow inherently more difficult to fingerprint than TCP, and is this really the case? And in this setting, we assumed a world where there's only TCP, and this is our TCP scenario. The adversary trains and tests and evaluates attempts to detect web pages in this scenario, and we do the same for Quick. A world which has only Quick, where every web page supports Quick, and the main web page will first be loaded over Quick. How does the adversary perform in this scenario? And what we found is that Quick is actually not inherently any harder to fingerprint than TCP. All of the classifiers that we evaluated perform nearly equally well in both the Quick and the TCP settings. Interestingly, though, we did find that it seemed that some of the classifiers performed perhaps even a bit better on Quick in the Quick setting than in the TCP setting, which may allude to Quick being somewhat easier to fingerprint than TCP. However, we suspect that this was due to the fact that at the time of running these experiments, the deployment of Quick was still in its infancy, you could say. So the variety of Quick server stacks was very limited, and so the amount of difference in what kind of samples would be seen across web pages, etc., was different. It could also be due to reduced middle box interference. But regardless, they are more or less similar in the the adversary's ability to fingerprint in both the quick and TCP settings. So given that quick is no harder to fingerprint than TCP, and given that an adversary must account for quick moving forward, must account for web pages being loaded with quick moving forward, how may he go about doing so? And so this is the next thing that we evaluated. And we evaluated two potential approaches the adversary may use to jointly classify quick and TCP. So in the first approach, he says, okay, web pages may be loaded with quick, web pages may be loaded with TCP. I'll collect samples of both. I will attempt to figure out, I'll attempt to train and teach my machine learning classifier on both sets of samples and hope that when it does see a sample in the wild, whether it's quick or TCP, it will make the right decision. And this we call the mixed classification approach. We also considered another approach, which we call the split ensemble approach. And in this approach, the idea is, well, given that the dedicated setting, in the dedicated settings, either the TCP setting or the quick setting, the classifiers perform so well. If an adversary is actually able to distinguish between the two settings, then he could just pass the sample to the dedicated classifier, and voila, he has pre-deployment of quick performance in his attack. But first, we'll look at the mixed classification approach. So here we trained on a mixture of quick and TCP, 50-50. And what we found is, as expected, so here the dotted line represents the mixed setting. And here we're showing the TCP and quick settings for reference. And so what we found is that, as expected, due to the increased noise in these samples, so because now the adversary has some samples loaded with TCP, has some samples loaded with quick, this is more variance in the data set, and this means that performance suffers. To counteract this, the adversary has to either collect a larger data set, or train his classifiers for a longer time. And this is one approach of overcoming this increased variance. The var-ceiling classifier, for example, seems to have benefited from that, albeit this is one of the longest training classifiers that we evaluated here. So what about this other approach, this split ensemble-based approach? So the first question we had to answer here was whether or not actually it's possible to distinguish between quick and TCP traces in a network. And so we created a classifier to do that. And this is in this setting, it's binary classification. So we take a sample and it's going to be either quick or TCP. And we used essentially a random forest classifier, which just spat out a confidence that this sample is TCP. And then with 1 minus that confidence, we take that sample to be quick. And we found that after only 150 samples, we were able to detect whether a trace was a quick trace or a TCP trace with over 99% accuracy. Looking into this, what we found was that this was due to the handshake, so the differences in the handshake, so both in terms of the RTTs for the connection establishment, so when these bursts of packets were going out, as well as due to the fact that for quick, the initial planned hello is actually quite large, whereas for TCP, it's actually quite small. The synapse handshake is quite small. And so this actually made it quite easy for the classifier to distinguish between the two protocols. So given that we can actually distinguish between the protocols, we can go ahead and create this ensemble. And so in the ensemble, the adversary is going to trains his TCP classifier on only TCP samples. He trains his quick classifier on only quick samples. And then he trains this distinguisher on both quick and TCP samples, and his job will be to distinguish between the sets of the two samples. Then when he encounters some sample in the wild, he passes it to all three classifiers. The TCP classifier says, well, I think this is YouTube with probability P1. The quick classifier says, I think it's YouTube with probability P2. And the distinguisher says, well, I believe this is more of a quick sample than a TCP sample. And then we do the weighted average, which allows us to, it's a safer approach for combining the predictions from both classifiers. And that forms a prediction for a particular web page. So this was our setup for the split ensemble, and we tested on a 1-to-1 ratio of quick and TCP samples. And we found that surprisingly, despite the fact that both the dedicated TCP and quick classifiers had very high precision, the split ensemble-based approach actually performed worse than the mixed approach. But on thinking about this, we realized that, well, it makes sense because even though there are different protocols, there is still actually some shared information in between these two sets of samples about that web page. So there are different protocols, but they do contain some shared information about the web page being visited, and the mixed classifier is actually able to leverage that. Whereas when an adversary splits the two data sets, he's not able to benefit from that. So in conclusion, the web is transitioning to quick, and this has privacy implications. Quick is not more difficult to fingerprint than TCP. However, if an adversary must account for it, or users will be able to evade classification by simply switching to quick. Joint classification of the both protocols is possible. However, this comes at a cost for the adversary, as to be expected from the addition of more noise or more variance or more variability to the network. And so he will either need to increase the number of samples or increase his training time to account for this. And finally, determining if a trace begins with T-Quick or TCP is currently trivial, and this can lead to attacks on a user's anonymity. For example, if an adversary is interested in 100 web pages, only 40 of which currently support Quick, then if he observes a web page which he knows is, if he observes a web page, he can already tell that it is not any of those 60 TCPs only supporting samples. And this can have further implications for the user's privacy. So with that, I thank you for your attention, and and I welcome any of the questions. Thank you.
Thank you very much, Jean-Pierre. Do we have any questions in the queue? Antoine, please go ahead.
Hello, Jean-Pierre. Thanks for the presentation.
Hello,
I have questions regarding the data that you use for classifying. In your slides, you present the training set and the tests on which you do the determination about the web page. How large is the training set compared to the overall data that you are using? This is my first question. And the second question is, are you doing your training and test on a page before it changes, or is there a drift over time? For instance, can you classify the web page with the same accuracy at point T0 or T0 plus 1 month, plus 3 months?
So to your first question, the split was, if I'm recalling correctly, it was 90% to 10%. So 90% of the samples were used for training, 10% of the samples were used for testing. And this accounted to something like on the order of, so 100 web pages, 90% of that. So it was usually about 90 samples per web page, so 9,000 monitored samples for training, and something around the same unmonitored samples. So a total of like 18,000. No, that's not true. 9,000 monitored and something like, I think, 40,000 unmonitored for training, and the rest for testing. There was some stuff there with making sure in the unmonitored set that the same thing doesn't end up in both the training and the test, etc., which reduced the effective size of the data set. But that's the first question. To the second question, we did not evaluate that with the quick and in the quick and TCP setting, but that has been evaluated by a number of authors up to this point. So I think it's realistic website fingerprinting had evaluated, and they found that actually by kind of doing a running collection of the web pages, so removing like the oldest samples and incorporating new samples, one could still maintain quite a high precision and recall for performing the attack. And there are also quite a number of recent works. Once I guess if I can stop sharing my screen and just speak while I am looking, but there are a number, I think 2 works which looked at, I think triplet fingerprinting is one work, which looked at how to kind of take a classifier and then just collect like 20 samples or 10 new samples and then get it back up to high precision, even though the original samples were collected months ago. So this really makes it easy for the adversary to keep the data sets still relevant well into T+1 month, T+2 months, T+3 months after he collected his original large data set.
Thanks for your answers.
And we have one more question from Matthew. Please go ahead, and then we'll cut the mic line.
Yeah, I'm just curious. When were your measurements actually taken? Like, or the real question is, if this was taken a while ago, are you planning on any follow-up work to see what the fingerprinting potential is as adoption increases for Quick?
So this was done summer 2020, the collection. Are there plans for follow-up work? Yes, but like most of my plans, things don't go according to them. However, I have gotten quite a lot of interest from other researchers in the past 3 or 4 months. So maybe 4 or 5 different research groups looking to also look at the website fingerprinting topic and Quick. So I would also expect some more recent works to be coming out in the next months, or year.
That's great, Jean-Pierre. And if you do have more results, please get in touch for a follow-up presentation if you're able.
Thank you.
That's great.
Yeah.
Thanks once again for your presentation today. Thanks a lot.
Thanks for having me.
Next up, we have Kyle Hogan on short tour. Let's just get the screen shared. Okay, that looks good. Please go ahead, Kyle.
Can everybody hear me okay?
Yep, we hear you.
Okay. So we actually presented this at the last IRTF meeting, and we're very excited to be back. I'm Kyle, working with Zach, who presented last time, Sasha, Ben, who's here today, and our advisors, Christina and Srini. So this is work in progress, and I'll be looking at the chat. So if anybody has questions, I'd be very happy to get them and answer them as I'm going. All right. So what, let's see, slides are not changing. All right, so what ShoreTor is doing is ShoreTor is a overlay for the Tor network that's intended to reduce latency between the relays on a circuit by making better informed routing decisions. And what we're going to do is we'll go over first the design of how this is working, try to evaluate it and say, are we actually getting better latencies? And then, of course, integration with Tor is important if it's supposed to improve latency on Tor. And then, as for any Tor proposal, security is also a goal for this project. And a reminder as we're going that this is work in progress. So I'd be interested in hearing feedback, and reminder that our measurement data set is incomplete. Okay, so the type of overlay routing that we're using is something that's more commonly seen in CDNs. And what this is doing is it's choosing these alternate paths when a direct route across the internet, and by direct route, we just mean the path that you would take by default, connecting over BGP. So this is like just the client server, they're trying to talk to each other. And this black path is going across, and some of the links are slow. And you as a normal person cannot just change the path you take across the internet. So instead, what CDNs will do is they'll in the middle actually connect you to different relays along the way and route you this way. And what this happens is it actually switches the path you're taking. So rather than orange connecting to orange directly, the orange client is going to make a connection to the blue server, and the blue server is going to forward their traffic to the orange server. And this is skipping, in this case, the congested links. Okay, so Tor actually almost looks like this already. The connections already contain multiple hops. What we're seeing here is we're seeing one circuit with all of the layers of the onion encryption and the TCP/TLS connections. So what we're proposing to change here is not this component, not changing the onion routing at all. We're instead trying to say that maybe some of these relay connections on Tor are actually going over slower paths than they could be. And if you can notice this, you can route them via a different Tor relay rather than directly to the next circuit relay. And what this can do is similarly to what it does for CDNs, is it will boost your performance. You'll be able to find a faster route, avoid congestion, etc. Okay, so this is a good point for anyone who doesn't get where this is fitting into Tor. If you can put a question in the chat and I'll get to it. So we'll move on then to when this happens. I mentioned it, but here's like what you'd expect. It's just only going to do this when the path between A and B, which are relays in a circuit, is actually like higher latency than the path if relay A connected to relay C, and then relay C connected to relay B. And remember, this is not part of the onion routing. This is not in the onion encryption layer. Yeah, so triangle inequality failure is correct. So this is specifically just on top of the already existing Tor routing. And to evaluate this, we actually need to know these latencies. And I'm very happy that I have this slide after listening to Mallory's talk. So this is our ethics interlude for how we are collecting these measurements. We've run our scheme through the Tor Research Safety Board, and we've been talking with them throughout the process, incorporating their feedback prior to starting measurements. We announced this to the Tor Relay operators mailing list, allowed operators to opt out. Some operators have opted out of being measured as part of this process. This is, of course, we were not able to get Tor relays to participate in this measurement directly. So we are running our own Tor relays and creating circuits using those to do our measurements. Our Tor relays are, well, we can't prevent them 100% from carrying other clients' traffic. We have very restrictive policies and bandwidth advertisements that effectively prevent them from carrying anybody else's traffic. We are also not observing, recording, or doing anything with anything we see about other traffic that is not our own. Okay. All right, a question. So since we don't know the whole path and this optimization on a per hop basis, does it mean that a Tor relay has to encapsulate so as to steer the packet through the right middle relay? Okay, so this is more of a design question on exactly how Tor is doing this. The answer to this is sort of. It depends on how you want to implement it. Right now, our proposal is that there's actually going to be an additional control plane packet, basically. So a new Tor cell with a command that's going to indicate that this is supposed to be a VIA packet. And these VIA packets are just going to update the routing information that relays already have. And the only thing that really needs to get skipped, and this is actually, so this is important, for people who are familiar with how Tor relays operate, we're skipping onion encryption. We are not skipping normal queuing. We do not want our traffic to sort of outcompete normal circuit traffic on a relay. And so we do actually want relays to, for the most part, process this special VIA traffic the same way they would process normal Tor traffic, with the exception that it should not be doing the onion encryption and decryption. Did that answer your question? Okay, so then here's what we have so far for the evaluation. Our current data set is approximately 125,000 pairs of measurements. We're focusing right now on relays with the largest consensus weight to start with. So our reasoning for this is, first of all, that these are the relays that are most likely to be chosen for circuits. The top 1,000-ish relays in Tor are present on about 75% of circuits. So like at least one of these top 1,000 relays is going to be on 75% of all Tor circuits. The second reason for this is that these large relays are the most likely to be online and responsive when we try to measure them, which is an important part of this project. We've actually been spot checking for now with some smaller relays and found that it's quite challenging to get them to actually answer an all pairs data set. So we can get some measurements, but we're not able to get smaller relays connected to every other relay in Tor to get the pairwise latency for completely. And that's it brings us to the future component of these measurements. We're not ever, we think, going to actually achieve a full all pairs measurement data set for Tor. Tor has very high churn. Some relays are going to go offline prior to the completion of these measurements. So we might get partway through it and then the relay goes online. It doesn't come back online again. And so we won't be able to finish that. Okay. All right, so here's our first set of graphs. So what we're seeing here is these are the pairwise round trip time relay distributions, shore Tor versus baseline Tor. And then below it is the first circuit. So we'll get to the circuits in a second. So the top one is just directly what we've been measuring. And what you're seeing is round trip times between these pairs of relays. The dark green is round trip times we've observed when just connecting directly as would be done in Tor. And the yellow is what we're seeing for if we're able to connect indirectly and it's faster, we do that. So the yellow and the green data sets are the same size. It's in terms of number of pairs. It's just that some of the pairs in the yellow data set are actually connecting via an additional third relay hop. I'll mention here, and this is more of a security point, we only do connect via one additional hop. CDNs connect sometimes via several. It's a little bit unusual. They're more likely to use one, but occasionally it is faster actually to connect via several. But for Tor, you need to avoid that because you can't actually loop through the same location twice, so you start to violate their security assumptions. So we're only able to do one. And okay, so this is so Benjamin, your question I'm assuming is for the circuits. So this is actually not a simulation. This is just directly measured latencies between relay pairs, and then summing them up to get the triplet latency. But we are not actually repeating the measurement through the third relay. So we're taking the measurement from relay A to relay B and relay B to relay C. And if that's a shorter path from A to B, then we'll insert that into this plot instead. Does that answer your question? Okay. Yeah, so for the circuits, the part that's simulated for these circuits is that we're using the Tor path selector tool. We've picked about 125,000 circuits. Importantly, only from the relays we actually have measurements for, because otherwise we can't plot the data. We're not right now wanting to try to estimate any of the measurements. So if we don't have a measurement from our own data set, we're not building that circuit. So this is sort of a skewed distribution right now, and it's important to remember that. But the reason I'm showing it anyway is because something that's very important here is you can actually see on this graph that there's some of these pairwise round trip times are over 10,000 milliseconds. And you don't actually see those in the circuits. And that's a little bit interesting because the circuits are actually longer, and you maybe expect to see higher round trip times. But Tor is picking these relays for circuits approximately based on bandwidth. And for the most part, the higher round trip times we're seeing in pairs tend to be lower bandwidth relays that are chosen less frequently for the circuits. So when we're picking circuits, we tend to choose the bigger, more popular relays. And so actually, just because something is showing up as really nice in the pairs data set doesn't mean it's actually going to be useful in practice, because maybe nobody ever chooses that pair. Okay. So is the circuit building entirely based on latency? Okay, so the question is the circuit building entirely based on latency, or is bandwidth also considered? For example, could a node with really fantastic latency, but a 10 kilobit per second link cause degradation for clients doing this sort of circuit building? Okay, so we're not changing circuit building. And that's that's going to be very important for security later. We're actually just strictly building circuits exactly the same way that Tor would. And then after a circuit has already been built, the relays in that circuit may choose to route between themselves, but not between the two ends of the client and the server via an additional relay. So the circuits are only looking at, Tor's selection, which is like bandwidth and family, like no relays operated by the same operator should be chosen twice, things like this. It's not looking at latency specifically. When we are choosing to route via an additional thing, we are looking only asterisk at latency. The asterisk here is that obviously no intermediate relay, no like via relay should ever take traffic that it can't hold. So if it's overwhelmed, it will not agree to be an intermediate relay. It will drop that request. And when the request is dropped, the requesting relay that says, oh, I'd like you to be this transit via relay, will know not to use it. It can never be sort of forced to do it. And then secondarily, we're planning to use Tor's sort of scheduling to make our via traffic lower priority than circuit traffic. And so it should never outcompete circuits that are like committed to this relay. These via connections are transient. If they start to slow down and not be fast, you just stop using them. There's none of this circuit tear down and rebuild that you would have by trying to do this sort of scheme with carefully chosen relays on a circuit. Does that answer it? Make sense? If not, I can come back to it. Okay. So this kind of like brings us cleanly into the integration with Tor a bit. Like I did mention, this is just an overlay. We're not touching onion routing. We're not touching circuit selection. We're not touching onion encryption. None of these are changing as part of this protocol. We do require modification to Tor relays. Tor relays need to support this proposal. This was actually a question we got last time at this meeting. And so I'm specifically mentioning it now because it is a little bit unusual compared to most proposals in this space. And the reason we think it's okay is going to be sort of on the next slide, but here's the like minimum requirements. The minimum requirements to actually benefit from this as a client is that you've picked a circuit where two adjacent relays both have updated to support this proposal, and that some other relay in Tor that has also updated to support this proposal can be used to provide a faster path between those two relays on your circuit than their direct route that was chosen directly with PGP. So it's really more about this like probability of selecting things that have chosen to update. And of course, this is higher when more of the network has updated. But I think as everyone is familiar with, Tor doesn't update that quickly. And so we're doing a little bit of analysis on incremental deployment. And for our currently small data set, what we're finding actually is that we still get pretty good speedups, even if only a small number of the relays in the data set choose to support the protocol. So what's happening here is that this is just so for pairs, the like darkest color here is if every pair in the set, everyone supports this. So we're seeing, let me also back up one second. This is in reduction in round trip times. This is no longer just the round trip time. So here, larger numbers are better. This is the speed up we're seeing. So if everyone supports it, we're seeing some quite large speed ups. As fewer relays start supporting it, so say like this purple is only the top 100 relays in our data set. So the largest in terms of consensus weight, 100 relays in the data set support this protocol. We're actually still seeing that some, small fraction, but existing amount of the pairs are getting like 500 millisecond speedups. If you go up to the 250 relays, we're getting some 1500 millisecond speedups. So we think that this protocol is actually going to be quite useful, even if really like only the large, more frequently used relays choose to update, and that most of the small relays never support it. Okay, so finally, security. We're not changing how clients select their circuits. So as a result, every part of this path, including our via relays, is completely independent of the client identity and their destination identity. We're analyzing security using the Mators framework, which looks at basically observation points on a circuit, and the probability that this observation point is useful in either identifying the client, their destination, or the connection between them. We're also looking at network share, and what we're referring to as network share is just the probability that some adversarial relay might actually see a larger fraction of Tor traffic when using our protocol than they would have as just a circuit relay in vanilla Tor. Finally, because we're not a circuit selection process, we do trivially support any alternate circuit selection processes that may be more security focused than Tor's current protocol. Specifically, maybe proposals that avoid passing through the same autonomous system twice or things like this. Okay, we'd like to finish our measurements collection, obviously. Right now, like I said, we have about, I think it's currently actually at 140,000. The top 1,000 relays all pairs is 1 million pairs. The full Tor relays is closer to 50 million pairs. And the reason I'm not giving you concrete numbers for this security slide we just looked at is that currently our data is just not representative. So we'd like to finish evaluating the security and effectiveness of this proposal once we have a data set that we believe is actually representative of the Tor network in its current state. All right, thank you. Any questions?
That's great. Thank you so much for the presentation, and thank you for coming back to the group to follow up on your earlier work. We appreciate it. And
yeah,
once
happy to be
again,
here.
thank you for yet again multitasking superbly and handling almost all the questions while you were speaking and doing my job for me. Do we have any more questions in the queue? Oh, I see one in the chat. Please go ahead and take
Yeah,
that.
okay. So would the data set be used by clients or are they used by the relays? The data set is currently a touchy subject, actually. So we are not sure if the data set is something that will ever be released in its complete form. There has been some recent work that's saying that latency across Tor potentially can be used to identify the exit relay that a client has chosen. And so potentially we're not sure. In practice, and because of that, the client will never see this data set. The client is actually totally agnostic to whether their relays in their circuit are using this protocol at all. And we think this is important because we really don't want clients to change their behavior because of this. We don't want anybody to behave differently from the majority of Tor users as part of this protocol, because this could make them more identifiable. So even if a small fraction of Tor supports our short Tor protocol, clients should not preferentially select those relays. Only relays will be using this protocol at all or are aware that it's happening.
I'm going to suggest we just take Watson's question as he's in the queue. So please go ahead with audio.
Description that you're avoiding the need to rebuild the circuit when you stop using VIA by no longer tying the circuit IDs to the connection. You have to do some intrusive work in Tor to break that. Is that right?
Yeah. So currently the plan is Tor cells have a header that includes the circuit ID and command field. And what we're planning to do is include two new fields to support this that are the prior relay on a circuit and the next relay on a circuit. And so what an intermediate relay is going to see is they'll now be able to learn where to forward traffic based on the next relay, and the next relay in the circuit that's now confused, like you mentioned, the connection is different. The circuit ID is no longer sufficient to uniquely identify this traffic. They will base it on the previous relay, so their last hop rather than the connection ID. And that will be enough and combined with the circuit ID to uniquely identify the traffic and route it correctly.
Okay, I think we have maybe 1 minute to speak to another question in the chat if you'd like to.
Okay, so there's a question in the chat on the use of latency introducing a bias that could allow de-anonymization based on knowledge of the network topology. So sort of, this is some recent research that's been saying that latency is heavily correlated with geography. And so fast paths tend to be short paths. And this has been a problem with proposals that are selecting, especially proposals that are selecting the circuit relays based on fast circuits, because now you're selecting circuit relays that are physically close to either the client or their destination. We have a less correlation because the circuit relays are still being selected at random just based on bandwidth, not on latency. However, I believe this is sort of saying is that by reducing the latency, it's becoming closer to the minimum, which is closer to the geographic distance. So in that regard, yes, this is technically making the round trip time of an entire circuit closer to the optimal, which is closer to the geographic distance between those 2 points.
Okay, thank you for that. I'm sure you'll want to follow up in the chat directly with the other questions there. Thank you once again for your presentation.
Yeah,
That was
thanks.
really great. Thank you. So moving on to the next talk, we now have a presentation by Tommy Pawley on private relay. Tommy, I believe you want me to run the slides. Just bear with me. Okay, does that look okay?
Yes, lovely, thank you.
Mm-hmm.
All right. Yes, I'll be giving a quick introduction to a new service that we at Apple announced recently called iCloud Private Relay, and I think, given a lot of the discussions that have already happened in Pearg about IP privacy and some of these earlier talks, I think this will be interesting for this group, and we'd love to hear feedback on how people could see this evolving and going forward. So next slide, please. All right, so what is private relay? This is kind of the name we've come up for this service overall, but it includes several different aspects, several different pieces of IETF-based technology that we're trying to put together. And overall, the goal is to have a solution that's promoting user privacy, specifically by separating out any cases where you have client IP addresses that are identifying users or their location, and separating that out from what origin servers that they're trying to access. It's not a full Tor or threat model, but as we were looking at things, this seemed to be a very, very common linkage of information that was used by many different parties to track users, and overall was really hurting user privacy. And so the pieces that we're putting together here, we have MASK, which is proxying over QUIC. The MASK working group is going to meet later today, so come to that if you want to talk more about it. We have some MASK proxies to fully protect traffic, and we're always putting these in multi-hop configurations, always more than one proxy. So kind of like what we were just talking about with Tor nodes. We're using oblivious DOE, so oblivious DNS over HTTPS, which is DOE that's being proxied. For all of the other traffic, so essentially you can have two modes. You can have stuff that you want to fully protect and stuff where you just want to protect your DNS. And then for doing the authentication to the proxies, these are just it's normal QUIC, TLS13, and we're using a raw public key to authenticate the proxy. And then in order to get access to the system, clients are authenticating using tokens that are RSA blind signatures. So we're able to vend out tokens to legitimate users and legitimate devices, but then when they redeem these tokens as single-use tokens into the system, they cannot be tracked as who the user was, anything about their device. It's a blinded token there. So next slide. So just practically, the scope of what we're applying this for now is in iOS 15 and macOS Monterey, and these are the versions of the OSs that Apple is putting out that are currently in beta. And for those versions, we're putting all of your Safari browsing traffic through, if you have this feature enabled, all of your DNS traffic, and then all of the unencrypted HTTP traffic on the system. These are kind of identified as the highest vulnerability traffic for both security and privacy, without kind of going full bore and putting everything through a proxy. And we're also using this as an underlying technology to protect against pixel trackers in Mail. So if you are loading any images in the Mail app, all of the remote content that's often used for tracking users is going to run through these same proxies as well. Next slide. Oh, did that go backwards? So forwards. Thank you. All right, so to get into some of the privacy goals and just talk about some of the design pieces we have here, I think we have 3 overall goals that I wanted to share with this group and kind of hear people's thoughts on. First, the main privacy thing is that we want no entity anywhere along the chain of your traffic to see both who the user is, based on their IP address, for example, as well as what they're accessing, be that the name of the origin server. So any entity along the network path until the user, they can of course log into an origin server, but no one can passively track who this person is and what they're accessing, either the ISP, the servers, or any of the relay infrastructure in between. We also want to ensure that the performance through this has to be good enough for just generic web browsing and for anyone, rather than having it be something where someone says, oh, I have to turn on my VPN or Tor and I know it's going to be slow, but that's okay. We want to push it to say, at least for these web browsing cases, people should not have to notice a difference. And then kind of along those lines, to really get a lot of these benefits over time, we wanted to make sure it's something that can be left on all the time as you're using it, and not something that you have to flip on and off like many VPNs. At least on our platforms, VPNs often have to be manually controlled. Users have to be aware of when they're on or off. And what we're trying to figure out is, how can we get to a place where, just like using TLS in your web browser is a given and a default, you don't have to say, oh, I want security now. How do we have privacy like this be a default? Next slide. All right, so to kind of go through the different things we came up for these goals, first principle we came to was that 2 hops is really going to be a minimum for the separation of data here. Next slide. So here's one of the diagrams we were working with. So if you have the status quo, you have a client talking through its access network, through the internet, all the routers, up to the server. And the 2 pieces of information we're particularly looking at here are the name of the server we're trying to access and the client's IP address. And right now, this is shared pretty much to everyone, and that's not good. Next slide. So in the model that we have, we essentially are always having at least 2 hops, an ingress proxy and an egress proxy. And very similar to how Tor would separate out data, the client IP address is only visible from the client through the access network up to the ingress proxy. It has its own encrypted connection there. It's forwarding along an encrypted connection to the egress proxy, and that only sees the server name, but not where the client IP address is coming from. And these 2 hops have to be operated by different entities, different companies, and the client is able to authenticate that, at least through what it knows about the key management for these different proxies. Next slide. Yeah, so in this, the client is responsible for selecting what hops it goes through, and it's controlling the fact that there's nested encryption to each hop, and it's managing that handshake. And as I mentioned before, the hops have to be run by separate entities. This is something in which the client gets a manifest of all of the different entities that run hops and is able to choose how to combine them. So in order to track activity that would require both of the entities here colluding, this is something that is more of a policy through the system that we kind of by contract are not going to be sharing the data here. And I see Jonathan in queue. Do you have a question?
Can you hear me?
Yeah. You're pretty faint, but I can hear you.
I'll try and talk loudly then. More of a comment, I guess. Mm-hmm. For a global passive adversary, unless you're adding cover traffic, they can track a user. They can identify them through both sets of the hop.
Yep.
Or at least, like in a theory perspective, it's impossible to prevent that without cover traffic.
And by global, you mean someone who's able to watch the traffic on both sides?
Yeah.
Yeah,
So global
absolutely.
passive.
So that is kind of not part of the immediate threat model that we're trying to address here. It's certainly still possible for someone to stitch everything together. What we're trying to do is say, is there a kind of an incremental step that we can make available to pretty much everyone, that at least removes the fact that today multiple entities are seeing all of the data, and it's just trivial for them to log as a web server all of your information like that.
Required to.
Yes. Good clarification. All right. Next slide. All right. So the other thing that we're trying to work on here is the fact that oftentimes people assume that having privacy is slow. We just heard a great presentation about trying to reduce some of the latencies that you have with Tor, but we knew that jumping to latencies like we would see like that often today would not be acceptable for a default stance for a browser. So next slide. So what we're doing here is trying to take advantage of a lot of the benefits we have through Quick and through Mask, and do many things to improve the latency that we have through this system. Part of that is just about the deployment of the various relays, making sure that they are optimally routing traffic between them and have a very good coverage of deployment throughout the world. Some of the other things, though, that I want to call out for, hey, Mask is very cool in this way, is as we're doing the forwarding through these different hops, we're able to take advantage of the fact that by proxying, we can get a lot of fast open connections. We're not doing full IP proxying here. We're proxying at the HTTP3 stream level. So if, in this case, if I'm talking to a normal TLS TCP origin server, I'm essentially just forwarding a quick datagram through the ingress proxy, very, very little processing there. It's a connect request to the egress proxy, which also includes at the same time the TLS client hello that we want end to end. And so the egress proxy is able to set up TCP to the server, send the TLS handshake, such that in essentially one RTT from the perspective of the client, it's able to set up a full secure connection to most any server. And it's not having to do DNS for that. It's not having to wait for the TCP handshake before starting TLS. Next slide. Yeah, so we're able to pretty much always do a fast open. And this really brings a big benefit. We're collecting metrics on essentially the normal resource load time that we're seeing across the browser. And in general, across the world, it's very much on par. And in some places, we're actually getting an even faster load than we would be if we're not going through the proxy. So this is not having a bad impact on normal web browsing. And there are a couple other side benefits here that you have by proxying at this level. We're actually able to be using Quick anytime your local network supports it, regardless of what the actual end server supports. So even though most servers in the world have not adopted Quick, the client's perspective is that almost all traffic now is using Quick. And the same thing goes for V6. Clients can pretty much always use native V6 to talk to the proxy as long as the network supports it. And so we're able to skip certain inefficiencies like what you'd have on a IPv6 only network, where you'd have to re-encapsulate or translate IPv4 packets. So in general, there are actually a lot of wins that we see by switching to this type of proxying. Next slide. And then last, I just want to talk about some of the design decisions we had to make to try to make this be something that you could have on all the time and break as little as possible, really with the goal of making sure that as many people as possible can use this type of privacy without having to turn it off. Next slide. So there are a couple considerations we had for creating exceptions for traffic that should not go through this. And these are things that oftentimes are not handled by VPNs that are on by default. So there's no impact on local network traffic at all. So if we detect that you're using a private IP address space that's going to route over your local link, that just doesn't go through this. That's not part of the threat model we're trying to address. We are doing a failover for anything that is detected as a private host name or an address. So this is important to make sure that if you are in an enterprise environment on an internal network, you're still able to access the private names, because we always would first check with the relay infrastructure. And if it says this is not resolvable in the public DNS, then we are allowed to try automatically on the local network. And then similarly, if the user has explicitly installed enterprise software to have a VPN or a proxy, we let that take precedence over this. So this can just be kind of the background default internet privacy level. Next slide. There's also a lot of interesting things we thought about for compatibility for existing servers. Right now, we're trying to maintain your rough IP geolocation. This is done by sending a client hint to the egress proxy that's in the form of a shortened geohash. So it gives you a square around roughly the region you're in. And then the proxy selects an IP address that corresponds to a city that may be in that region. So it's definitely better privacy than you have before, but the user, if they want, can preserve some location. And as we're looking at this, I think we recognize that there's a lot of need for more standards work to be done in the area of geolocation and how that's shared with permission, and how to maintain fraud prevention mechanisms in the face of IP address privacy. Next slide. Yeah, next slide. So going forward, we're using MASK for this. We'd love to see more expanded support for MASK by other vendors. We'd love to see an open and interoperable network of these that would help privacy for all users everywhere. I think there's interesting models we can imagine of having ingress proxies move into ISP and carrier networks to make sure that they are very optimized. We're already hosting some egress proxies within content provider networks to make sure that it's very accessible and very quick to get to your content. And there's a lot of interesting work to do that I think we'd love to learn from the Tor community about how you discover hops and choose interesting routes through the network. And next slide. Great. So I just wanted to end. So we have a couple minutes left for questions.
So Victor, do you want to go ahead, please? And I know Steve had one he put in the chat, but we'll bring to the queue as well.
Hello?
Yep, we can hear you, Victor.
Okay. The authentication of the origin server, is that still end-to-end, or is it, authenticated by the proxy in some sense?
Everything is end-to-end. The only thing that would be between the proxy and the origin would be a TCP handshake, but everything on top of that is end-to-end. And in the case of quick origins, it's fully end-to-end.
Okay.
And Stephen was next, please.
The chat already. I don't know if my audio is going to work this time, but
it's choppy.
Somebody else can read it out from the chat if my audio is not working. Okay, so I guess I'm just with the longer term, not the short term. The longer term is between kind of putting a bunch of complicated parts like this versus a concept, but probably harder to deploy thing like Tor.
I think you're breaking up too much, Stephen.
But those kind of longer.
I think we've lost you, Stephen.
Yeah, right. So I see his comment here. How would you characterize the longer-term complexity trade-offs between this approach and trying to eventually move to something simpler, more generic, but harder to get deployed like Oliver Tor? I think I don't actually think there's a terrible amount of complexity in this. It's just, you know, a one particular protocol. So I guess what I'd like to see is, you know, let's try to figure out collectively in standards and industry, what solution do we think makes sense to be deployed all over? And I think mask proxies is a good starting point. And seeing that converge with something that's compatible with Tor would be very interesting.
I'm going to cut the mic line. Hopefully that answers your question, Stephen. Matthew, please go ahead.
Yeah, so I have 5 questions, but I'll start with 1.5. Are you using DNS for key management, and are you hard coding the list of relays, or are you using something else?
Yeah, right now, the public keys used for authenticating the proxies, doing oblivious to, all of that is coming from kind of a control plane server from iCloud that the device checks into. That's very much a kind of a short-term practical decision for this feature. And I think one of the interesting areas to look forward to, especially for standardization, is making that more open and discoverable and extensible in a maybe DNS, maybe some other type of public log.
Thanks.
Andrew is next.
Hi, yeah, I hope you can hear me. Just a quick clarifying question. You mentioned RSA blind signatures. Is that using the approach in the draft going through CFRG at the moment?
It is exactly that draft. That is one of the reasons we are very interested in that draft.
If Joseph, if you have a very quick question, so I had cut the mic line, but if you want to jump in real quick. Oh, no, I think, or if you can take that to the chat, that would be great.
Good.
Yep, I think that question is going to go to the chat for you. Okay. Tommy, thank you so much for that presentation. Really appreciate it. Okay, so let me stop sharing. And next up, our final presentation is from Josh Carlin on Flock. So please, do you want to share your screen with your slides?
Yeah, I'll share my screen.
Yeah. Okay, you should be coming up now.
Two seconds.
Okay, that's good. We see them now. Great.
All right.
Thanks.
Actually, just forgot the presenter slides. Sorry, can you accept the screen request again? Thanks. All right. So I'm Josh Carlin, Tech Lead Manager and the Privacy Sandbox team at Chrome. And thanks for having me out to present on our work. I really do appreciate the opportunity. For those that don't know, Flock is a project in Chrome's Privacy Sandbox, and it just wrapped its origin trial. I'll walk you through the technology behind that trial. And we're also chewing on the feedback that we've received from the trial. So I'll talk about some of our thinking about what comes next. So in order to talk about Flock, you have to understand what browsers are doing and where they're heading. Research has shown that up to 52 companies can theoretically observe up to 91% of the average user's web browsing history. And greater than 600 companies can observe at least 50% of the user's browsing history. We'd like to stop this highly detailed and pervasive tracking of users across the web. And the first step is to start building walls. We're building walls between the sites that users visit. What happens on pages of site A stay on site A and aren't known to pages of site B. It's a significant amount of work. We need to partition everything in the browser. Resource caches, DNS caches, cookies, JavaScript storage, socket pools, TLS session identifiers, everything. And I just want to be clear that when I say we are building walls between sites, what I mean is like the registrable domain of the URL that's in your URL bar, like so the main frame of the site, which is in the URL bar, it's that registrable domain. That is what I mean by the site. Building these walls is the right thing to do, and we're hard at work at it. But it has to be done responsibly. Lots of important use cases are affected when third-party storage disappears, including logged-in behavior on third-party widgets, personalized advertising, measurement fraud, spam detection, even simple things like logging out across sites with federated login, etc. So to promote the free and open web, we need to ensure that we don't lose these important capabilities. For instance, 50% of programmatic ad revenue is at stake for sites. Chrome's Privacy Sandbox is attempting to provide for each of these use cases while providing large wins for privacy. I won't read the list, but you can see that we have a lot of ongoing research effort. And I'm just going to talk about Flock, which is a small part in the larger Privacy Sandbox effort. Flock is focused on interest-based advertising. Interest-based advertising collects the topics of the page that the users visited to form a user profile of interests, which then allows ads to target a user's array of interests instead of the context currently available on the page, which might not be particularly valuable. The goals of this project are to support interest-based advertising in an easy-to-use way, while still making it hard to track individual users online. When I say easy to use, I mean that advertisers can use similar technology to what they're already using so that it's easy to transition to, which greatly increases the chance of success and improves privacy faster. So how does interest-based advertising work today? Today, websites load ad tech script onto their page, right in the main frame. And that script gathers some contextual information and sends it to the backend server as part of its ad request, along with a user identifying cookie. The backend adds the current context to its profile for the user and selects an ad based on this profile to respond with. With Flock, the flow is similar, with one fundamental difference. Since there's no longer a third-party cookie, because of the walls we're building, as I mentioned before, instead, ad tech is provided with a group ID, a cohort, where interest from the sites visited by this group of users are analyzed, and a predictive model is built to determine which ads are used in a cohort and are likely to be interested in. The advantages are the user's browsing history is analyzed as a group instead of as an individual, and the ad tech backend requires few changes. This is what the API looks like. It's a single call, document.interest cohort. It's async and returns a promise. When it resolves, you read a dictionary value that has a version and a cohort ID. The version is there because we expect Flock to iterate before we and the ecosystem are satisfied. Plus, even then, we'll still need to update things. Note that sometimes the API rejects, and that rejection can have many reasons. So rejecting in and of itself is not giving away much of anything about the user. For instance, the user could have disabled the API, the user could be in incognito, not have enough history to calculate, could have cleared history, could have cleared cookies, etc. So this is a research group, so let's go into a little bit of detail about how a cohort's actually produced. To begin with, it's done entirely client-side, with the same data that's used to store user browsing history. No new data is collected. And the only part of the history of URLs that is used are the domains of the URLs. We're not looking at the path, we're not looking at the contents of the pages, we're just looking at the domains. Some other desired properties of cohorts are that it should have thousands of users, it should not reveal sensitive information, and it should not provide significant fingerprinting surface. Now, let's talk about the details. What we're trying to do here is to take the registrable domains from the user's browsing history and reduce them from a very large number of dimensions to 16 bits, where the distance between the input values is preserved and the relative distance between the output values. Now, locality-sensitive hashing excels at this. So we first encode the user's history by taking the registrable domains of eligible pages and hash them into 64-bit values. And then we place them into a sparse vector with ones where the hashes of the sites were and zeros everywhere else. We then use SimHash to reduce this vector down to 50 bits. Again, the distance between input items should be preserved in the output of the SimHash. And finally, we apply a mapping provided by a Chrome server that groups adjacent SimHashed values together to ensure that there are at least several thousand users in each cohort. This reduces the dimensions down to 16 bits. So that's it. No smarts. It's all client-side, no ad tech logic, just a dumb dimension reduction and some merging of neighbors at the end to ensure that cohorts are large enough. Okay, so which pages are included in the cohort calculation? Not every page. The idea was that only pages that use the API would be included. And even then, only if they weren't using private IP addresses and if the page hadn't opted out. Now, for the origin trial, we were concerned that the data wouldn't be representative for early adopters, since these early adopters would be the only ones triggering the API, and their intent was to try to figure out if this was an API that was useful to them. But since they were the only ones using it, and there were a few of them, and origin trials specifically require that 0.1% or up to 0.5% of traffic be within the origin trial and be within using the API, the usage would be severely limited. So we decided to include pages with ads on them as well in the origin trial as part of the input to Flock. Pages with ads are ones that we considered most likely to use the API. All right, so let's talk about some of these characteristics we wanted. We wanted the cohorts to be k-anonymous. We ensured that there are at least 2,000 Chrome sync users per cohort. So the actual number per cohort is actually higher since not everybody uses sync. Chrome's researchers anonymously gather the sites that people in different cohorts visit from sync users in an effort to try to reduce the amount of sensitive information that might leak. So if a cohort is more strongly correlated with a sensitive topic than the general population, then the cohort is added to a list of revoked cohorts and get distributed to clients. And you can see the analysis, or the results of that analysis here. On the x-axis, you have t-closeness. If the fraction of users in a cohort that have visited a sensitive page is higher than the general population, then we revoke the cohort. The further to the right you are, the further cohorts can be from the general population for a given sensitivity. And on the y-axis, you have the fraction of cohorts you'd have to block to maintain that t-closeness. So we chose t-closeness of 0.1, which you can see is sort of in the closer to the left side. And we had to drop roughly 4% of cohorts. There are, in this origin trial, quite a few parameters. And for some reason, several of them landed on 7. Flock is updated once every 7 days, including data from your last 7 days. And you must have had at least 7 different sites in your history to get a cohort. We ensured that each cohort had at least 2,000 sync users, and users could opt out via the Privacy Sandbox UX. So that was a recap of the origin trial and what we just wrapped up a few weeks ago. So now let's talk about the feedback we received. We received lots, which we're grateful for, especially to Mozilla and their thoughtful privacy analysis of Flock. It's an incredibly valuable bit of information, and this is the process working as intended. So now let's transition from talking about the completed origin trial to how Flock might improve in future iterations based on this feedback. These ideas are still being evaluated, and none of this is locked in. We plan to discuss these ideas in the open, refine them, and test them to better understand their privacy and utility. So let's go through the feedback one by one. First, let's not opt into sites with ads and experiments. Done. We'll fall back to opt-in only via usage of the API. That's what we wanted to launch in the end anyway. Second, cohorts are hard to understand for end users and even technologists, right? We started seeing comments along the lines of, oh, Flock is going to reveal that you like green sports cars, you mowing the lawn, and like a particular kind of window shade. it just simply was not nearly that specific and couldn't be. So, but that was still hard to express and still hard to understand. So given that the API is about user interests, it might make sense to stick to topics instead of cohorts, right? And a topic could be something like beauty and fitness / fitness, as opposed to a cohort like 21854. And topics have a number of advantages over cohorts. Users can see what's being said about them and understand it. Each topic can be human vetted for sensitivity. The topic taxonomy can be shorter, like say 256 topics, as opposed to the roughly 30,000 cohorts. So there's less fingerprinting surface as well. And users might be able to opt in or out of particular topics. And I should note that we're not the only ones thinking about this. The Privacy CG is talking about add topic hints, which is an alternative API to Flock meant to address interest-based advertising and is also based on providing interest via topics. The third issue is that Flock adds new fingerprinting service, and this is true. Note that today's fingerprinting service, even without Flock, is easily enough to uniquely identify users. And part of the Privacy Sandbox's goal is to reduce that fingerprinting service and budget its usage. Nonetheless, we'd like to add as little new fingerprinting service as possible and still be useful. And we believe that there is more that we can do. First, if we go with this notion of topics, then we are already providing 8 bits instead of 16. Second, we can add in random topics with some probability. So for a given week, you might give a site instead of one of the user's topic, you would just with 5% chance say, actually, we're going to give you a totally random topic. Third, we can give different topics to different sites. This actually has a pretty significant impact on cross-site fingerprinting. For example, you could take the user's top 5 interests instead of just the top 1 and give each site one for the given week at random. And the chances that 2 sites see the same topic for a given user is only 20%. Taken together, we think these mitigations could dramatically drop the usefulness of Flock for cross-site fingerprinting. Regarding sensitivities, this is significantly improved by means of having a small curated list of topics. And perhaps this list could be maintained by an external organization. To stay on the safe side, we'd likely continue to monitor topics for sensitivity with T-closeness analysis as we did before. And another area we consider improving is the scope of Flock. As designed, there is a single cohort or set of topics, depending on the direction we go, that is derived from the user's global browsing history. This is beyond the scope of interest derived from third-party cookies, which are limited to the pages that the third party was present on. One option we're considering is to provide a per third-party set of topics based on the pages that the third party was on, and then calling document.interest cohort from. Then we could say that Flock is 100% a subset of the capabilities of third-party cookies. This also has disadvantages, namely that if multiple parties can retrieve their topics on one page, that dramatically increases the fingerprinting service. So we'd have to counter this by limiting the number of topics readable on a page, or a site rather, to a given, to like 2 or 3 per week. And while mitigated this way, it does still increase the fingerprinting risk over global values. So that's it. For more information, we have a GitHub page with our issue tracker and our explainer. We intend to ramp up our conversations quite a bit more. We're going to have, I hope to have phone calls started soon. That'll be every other week or so. The Privacy Sandbox overview is available at privacysandbox.com. And then for more details about the Flock origin trial and all its specifics and technical details, please see the specific Privacy Sandbox Flock page. And I'm happy to take questions.
That's great. Thanks very much, Josh, for that presentation. Do we have anybody with questions in the queue? We have Jonathan. Please go ahead, Jonathan.
Verification on what the client submits. So could I just completely submit a random string for every website? A random bit string?
So the client has its cohort determined by the browser, which then gets sent. If you wanted to override the JavaScript API and have it return a random value, you absolutely could. If you disable flock via the UX, then what happens is that you just don't have any flock sent. It rejects.
Information about me, whereas just returning a random string, it's very difficult to put me in a group that says, oh, this is a person who always has it off.
That's right. That group, so that is actually another thing I should say that is totally up for discussion is, do we want to return nothing or do we want to return a random value? And I agree, there's actually a lot of privacy gain to having a random value, and that may be something we do. There's also advantages to being in this group of users that have it off, because that group is not small. And it does provide, it makes it easier to train on the advertising side to understand, like, do these topics or cohorts have meaning, right? So it dilutes the meaning if you make it random, and we are doing some 5% random. And the number of users that actually can't have a cohort for one of a myriad of reasons is actually fairly high. So we don't want to completely like drown out the signal.
Okay, thank you. Watson, you're next in the queue.
Thank you very much for your presentation. It was pretty informative. I'm not seeing the justification for leaking information about user history beyond we're already doing it today and we need to support this use case. Well, it's not, you know, it's clear that there's a considerable number of consumers who don't want to see advertising, who install things like AdBlock, etc. And so I'm not sure what and there are more privacy preserving ways of doing advertising where the interests are not being sent to a third party to determine what ads are being displayed. So I'm not sure why we're gathering information that's extremely sensitive and sending it around, because even like when you talk about sensitive topics here, a lot of these are ones that are very visible from the browsing data and potentially have significant consequences here. So it's not like, what's the justification for the user to have flock on?
This is from Chrome's perspective here. This is a part of like keeping the web open and free, right? If sites can't monetize, then we wind up with silos. So we're hoping to keep especially tail sites and all sites open and freely available. And it turns out that personalized advertising is a huge chunk of change and something that we feel needs to be supported. If you don't want to have that, then feel free to disable. It is very easy to disable.
Okay, does that answer your question, Watson?
I would need to see a lot more data. We can't just, I mean, display advertising worked for many, many years to support the news industry. That doesn't require having information about user identity. And it's not clear to me that users understand the consequences. There's a great incentive in making sure they don't understand the consequences of what Flock is revealing. And, you know, when we talk about free and open, we need that's not about, it doesn't to me mean you can make money off it. To me, it means that you can put websites up and you don't have to worry about your privacy or security being violated. These are much more important questions than who exactly is making money, how do the slimiest people on the web continue to have a living. That's not as, I don't think that's as important.
Okay, Matthew, you're next up. Please go ahead.
Sorry, was that me?
Yeah, I think. Go ahead.
Earlier in the presentation, you talked about the origin trial and the basically compressing the hash map using SymHash. and there was a mapping that was distributed by Google. Is that something that would be standardized, or would that need to be recomputed occasionally?
So the intent was, now things are changing since we're talking about new directions, but the intent of that mapping sent from Google to clients was to do two things. One was for cohorts that we deemed to be sensitive, we wanted them to not be used by clients. So that list would remove sensitive cohorts. The other purpose of that list was to ensure that groups were of a certain size. And so, you know, squish together neighboring values. And that is something that would have to be done on a regular basis. We expect, you know, the web is dynamic. We expect sensitivities to change over time. We expect the sizes to change over time. So in our minds, that would be a thing that would be done on a regular basis and distributed. That is absolutely something that we had full intention of sharing and anyone could use. And if there were, like, if we could standardize on what that looks like, then we're all for it.
So I'm just going to jump in. There's almost a very similar question in the in the Jabber chat, which was, what is to, this is from Stephen Farrell, what is to stop topics being used to censor or imprison people, e.g. an LGBT topic in many countries is okay, but in some it could get you locked up?
So I think geographic, what's what I'm looking for. Different geographies have different sensitivities, like, for sure. I think that's important. We've gotten that feedback, and I think that needs to be taken into consideration, absolutely, and how we choose which topics would be included. And it may be geography specific. Or I just remove it altogether if there's any chance of it being sensitive. Like now, and that's a hard thing to say because I understand, and lots of things can be sensitive. But that one in particular is easy. We all know that can be sensitive, and that would never be a possible topic.
Thank you. And where's your question, please?
Thank you very much. So if I understand this from a very high level in terms of what's going to eventually be offered to the user, you know, won't have a choice to say don't be tracked. So my fundamental question is, what's going to happen to the do not track checkbox? Is that actually going to go away, and the user will be forced to pick between full tracking with no anonymity or tracking only through this aggregation process?
Sorry, I'm not quite following. So do not track just adds a header that everybody ignores, as far as I can tell, and also as a
That's fair.
So that's the reality of that. What we are offering is if you would like to use the Privacy Sandbox and all of its tools or individual APIs, you can enable or disable them. If you don't want to have Privacy Sandbox, you can disable it as a whole. We still will offer blocking all third-party storage and cookies. So you can have, like, you can customize it to your needs.
All right, so you still allow users to put up the walls
Yep.
that sort of the blockades.
Yep, absolutely.
Okay.
So I think that's all the questions from the queue. There was quite a bit of discussion in the chat. We're at time now, but if anybody wants to follow up with anything specific there on the list, hopefully Josh is able to answer some of those questions, potentially via the chat or the list if you're able to.
Yep, I'll take a look.
Great, thanks very much. Thanks for the presentation. So that's a wrap for us today. Thank you for joining, everybody, and enjoy the rest of IETF.